For an engineering quote, just send construction documents to info@jeistructural.com or check us out online at jeistructural.com. Look forward to working with you.
Good morning, everyone. Today, Juan, Pablo, and I are going to present these lessons learned that we called multi-story Mullion challenges. On a recent project that we had with a multi-story curtain wall, we had some challenge related to the RFI building movement. Some of the challenges were we had whole curtain wall frames with high wind pressures that were, this project is located near to the Texas coastline. We had large service loads, vertical deflections at each level of the building. We had a strategic splice placement to reduce moment and deflection demands on mullions, and vertical mullion top and supported on horizontal mullion. Some solutions that are provided in this project are option A, stack curtain wall frame to dead load at the seal. Request information from the EOR was required. Option B, relocate the splices and modify a wind load and dead load anchor as required. And for the other vertical mullion and top end supported at the horizontal mullion, we had a detailed movement joined between the vertical and the horizontal, allowing the shear block to slide into the vertical and detailing a silicone joint between the horizontal and the vertical mullion. So on this page, we can see the location of the frames that we are analyzing. As shown, this frame spans multiple levels. Let's show here in creating tall frames with splices and mid-span anchors, as we will explain below. So here we have an detailed elevation view where we can clearly see how the frames are located from the level 3 to the level 8, like these curtain walls. Once we received the response from the RFI, we were requested for the building movements at each level. A detailed study was carried on the challenges that I mentioned at the beginning of the presentation. Okay. All right. Here we have the view of the frames in the shop drawings. We have marked each level with its respective deflection, showing that initially we have a distribution for wind load anchors and dead load anchors with the following movements. We have 0.4 inches of deflection for levels 4, 5, 5, and 7, and a deflection of 0.29 for level 4 and level 6. Okay. Now, the importance of this analysis is as seen in the detail of this mullion. We have a clearance space here. We have this maximum allowable movement of 3/8 inches, a maximum movement, which is less than the movement that we had in several of the levels, as we saw earlier. So keeping this in mind, we can proceed with this analysis that is useful to take decisions later. Okay, now let me explain a little bit about this diagram here. The red lines represent the mullions below the splice near to the level 4. The green lines represent the mullions between the splices at the levels 4 and 5. The blue lines represent the mullions above the splice of the level 5. And the orange, yellow, and cyan rectangles represent the glass between these mullions. Having explained that, now I'm going to talk about these two cases, scenarios to consider here. For this mullion outlined in green, since the red mullions are supported at the seal here, and they will remain static while the slab at the level 4 above the splice deflects. We will see the following movement in the Mullion, like something like this. So in this case, if the movement exceeds the Mullion's clearance, we would even end up resisting on the glass, transferring stresses to it. And for this second case, to be conservative, we would consider a case where the slab of the lower slab deflects while the upper slab remains static. In this case, we would see the following movement in this cyan mullion, like this, something like this. And the glass marked in cyan would move downward, reducing the bite it has with the horizontal mullion. In this case, well, the glass would not actually fall out of place since it will still be supported for the vertical and the lower horizontal mullions. We would face the problem of water infiltration. And with all that explained, the challenge for this project, and hoping it was clear, Juan Pablo will continue with the lessons learned to explain the solutions on this challenge. Thanks.
Let me share you my screen. Do you see the same blue beam?
Yes.
Yes,
Okay.
we do.
So as Kevin was saying, we have those challenges, and we talked to Javier to see what the best options for us were. After a long talk, we have two solutions. The first one was option A, as you can see here. Mullions will be stacked at the full height of the elevation using hairline hard splices. So, in other words, all the dead load will be going from all the full height of the frame till the seal. We calculated the dead load, and we have 1.05 kips per jam, and for each intermediate vertical we have 1.75 kips. The important thing in this case is that we have to request a confirmation that from the EOR that the substrate below these frames will have the capacity to sustain this kind of dead load. So this will be the change. All the midspan anchors will change from dead load to wind load. So in that case, the slot on the midspan anchor can have the capacity to accommodate the slab movements. So we change in all of this from dead load to wind load and doing a hard splice of 0 inches. So that was the first option of analysis. And I said to Javier this was good because everything worked, and according to my, if the EOR said this was okay, it will work. And Javier told me, but let's give them another option. If you saw like what Kevin showed, the deflections were spaced. For example, here was 0.2, and here was 0.29, and here was 0.4. That is the same level in level 5 here. And level 6 was 0.29. So speaking with Javier, we agree that we can give the client another option. Move the splices so the wind load midspan anchors can accommodate where we have the maximum movement from the slabs. Therefore, we changed, for example, in here we have 0.4, but it was wind load. So this kind of movement, we will be able to accommodate it in the wind load anchor. This too was a dead load. So for 0.29, if our capacity was 0.375, it will be okay. But this is the case we start changing because we have a movement of 0.4. So as Kevin told us before, the glass will be in contact with the horizontal. So we tell the client, if we change this to a wind load, the wind load anchor with the slot may accommodate this kind of movement. So we change the splices and the location of the splices and the lengths of the mullions to accommodate for where we have 0.4 slab movement, we have a wind load anchor. For our luck, the client said to us, no, EOR likes to dead load in the seal, so we put for all these frames hard splice, only wind load anchors, and dead load in the seal. Then the next challenge that Kevin was telling us about is that for frame 16, we have almost the same distribution for all the other frame that I told you before. In this case, the movement was really small, but the challenge was that in here, we had some intermediate vertical mullion that doesn't go from seal to the header. It stops here. So we changed this jet load and we include a wind load here, making this splice not exist. So with this wind load, we can accommodate that in here, all other vertical mullions have a dead load anchor. It will have a dead load anchor here. When the horizontal goes down, it will crash it. So we put it a wind load and we put a joint, a halving joint, making that the horizontal and this vertical will never touch. So that was one of the challenges that we also have, because normally the vertical will go all the way up. And that was the challenge that we have on this project. I hope you understand what we did.
Two things that I wanted to add to the project was emphasize the importance that every time we're changing the amount of dead load that the structure behind us is going to receive, is always a good idea to instead of making the assumption that we're okay, always as early as possible reach out to the client for a request for the EOR to look at our modified load path and modified dead loading, because it might very well be that the structure below the frames don't have the capacity to resist the additional dead load. So that's why for option A to work, that was the most important step, basically. And for option B, like when Pablo was saying, we basically bypassed the high movement areas with a wind load anchor, relocated some wind load and swapped some wind load by dead load, moved the splices around a little bit. That option had the least impact as far as load transfer goes. So in that one, we didn't really need the EOR's approval. So just wanted to emphasize how important for this to work was to get the EOR involved as early as possible. So as Juan Pablo was showing the detail for the cover, and we had some pretty substantial weak axis load on this moment in this mullions, and being a project close to the coastline, the wind load pressures were upwards in the, how much was the cornerstone pressure? Remind me, 49?
Yes, 40, I think.
Yeah, so pressures were high, as we typically see in coastal Texas. So we were discussing with Stuart how to apply the wind load on these extensions to the mullion, because it would be overly conservative and unrealistic to apply the full design wind load, because if you show on the left screen the floor plan, Juan Pablo, as you can see, the corners of that building offer what Stuart called a wind shadowing opportunity for us to shield those frames and not apply the full corner zone or even zone 4 wind load. On the screen on the right, we would be considering wind going on the up and down direction. So we originally wanted to get everything to work with applying the full perpendicular load, like in the direction normal to the frame, in addition to a parallel wind load event that would simultaneously load the cover. We quickly ran into problems, and the weak axis capacity for stress and deflection was really a limiting factor. So we rationalized, we tried to use some engineering judgment, and with the help of Stuart, we came up with a reduction of 50%. And I think how we landed on 50% was, okay, we took the approach of saying how much wind could we actually resist before the deflection on the weak axis becomes an issue. And it came to about 50%. So this was presented to Stuart. He was going to originally be the one stamping this project. So another important item here is when you're making these types of judgments that are not necessarily covered by ASCE or any other prescriptive code, always run things by the ceiling engineer to make sure that she or he is comfortable with that approach. In this case, Stuart, he actually had suggested to use a reduced 50% of the zone 4 pressure to be applied on the fins. I believe CW17 in the screen on the right, if you zoom in a little bit on that one, you can see the fins there on CW16.
Yeah.
Yeah. So that pretty large corner, yeah, that box on the corner of the building goes the full height of the building. Stuart agreed that there was going to be some sort of wind shielding effect because of that, of the building geometry there. And after having this discussion with Stuart, we applied only 50% of the zone 4 pressure on those, and we got that to work, and that seems to be a pretty reasonable assumption to make. And I might ask around the group in Kansas City if they've come across any type of situation similar to this in which an assumption was made that we can reduce the parallel direction load. So yeah, with that, I believe, unless Kevin and Juan Pablo have anything else to share on this project, we'll bring it back to the table for discussion and questions.
Yeah, I had one question. Did we consider splicing in the vision area, and why not?
I believe we did. It was just the combination of the wind load, the combination of the service load deflections didn't really allow for those splices there. Like on level 5, for example, you have 0.4 inch movements. Yes. If we would be to put a splice on those spandrel areas, we would still run with the glazing pocket clearance and bite limitation that Kevin presented before. But that's a good point. We always want to try to use spandrel areas, which are typically right underneath the slab areas, to hide those splices. But in this case, because of the live load movement, it wasn't an option.
So what's another potential reason why we can't splice in the vision? It's a structural reason. For anybody.
I'll let the table discuss that one.
Can you repeat that question, Matt?
So why can't we splice in that vision area? At least how we have it.
I think the splice is on the spandrel though.
Yes, it's here.
Or sorry, in the vision area.
Yeah.
I mean, my first thought on that, Matt, would be the farther you get towards the center between the anchor points, the larger the deflection is going to be. So that expansion splice is going to open up. It's going to cause a pinch point on the glass, which could easily shatter the glass.
Yep, and that's one good reason not to do that. Still another one. Can you move over to the actual elevation and zoom in like on the floor line area where we have the spandrel?
Of course, give me like here?
Just on the actual frame right there. Look at the horizontal right below the anchor points.
This one.
Can you go to that? Yeah. Can you go to that detail?
Of course. Give me 1 second. I have bad memory. This one.
What's our issue there?
Are you referring to the sealant?
Yeah. So if you splice below this horizontal, your glass is still adhered to frame above and below the splice. Actually, it's resting on the horizontal below, and then it's siliconed up the next horizontal above. So if there's any movement, there's no way to really accommodate that in this type of with this type of a horizontal. You'd almost need to put that splice directly below the horizontal, and then have the top of the glass freely floating right there. But yeah, watch if we have SS also with verticals. Stay away from splicing an SSG vertical with an expansion joint because again, your glass will be adhered above, below the splice, so there's not any way to accommodate that.
What about a hard splice?
Hard splice is fine.
Okay,
It's just when we have the move.
right.
Yeah. When you do the hard splice route, think about the whole frame is moving as one huge piece. So there's no differential movement within the parts of the frame. The sealants are not tearing, the glazing pockets are not being maxed out. Everything, if the sill moves up or down, the entire frame moves up and down. Now, we do need to pay attention how tall can our wind load clips get, because on this particular situation, because we were stacking the full height of this mullion, we were having some considerable thermal expansion movement. I think it was in the order of 1.2 inches of thermal. So the edge of the slab, the pour stop, might only allow for a given height of a wind load clip to be, and if that's a limitation, there are other options like welding to the underside of the slab, and in that case you can put an angle flip to its side and with a long leg attaching to the mullion. There are other alternatives to get around that, but that's something to consider too.
So I'll add that I'm very happy with this presentation. I think Kevin and Juan Pablo killed it. The explanations, the visuals, this is going to be great for training in the future. The other thing I've done in the past on these types of projects is always see if there's an offset tongue. So Juan Pablo, whoever's got the control of the screen, can you show
Yes.
that horizontal that's at the dead load clip area?
Of course. This horizontal
Yes.
is this one, the one that.
So 9A.
What I have seen in the past and asked for is, can
If-
we get a horizontal where instead of having the tongue directly in the middle of the mullion, where it's offset a little bit so that we can accommodate, and I've seen some that can accommodate up to a 1/2 inch movement, but I think those go up to a 3-inch sight line instead of a 2.5. But with that offset, it gives us more room in the glazing pocket for that movement. They're not always available, but it never hurts to ask.
Yeah.
You could also do like an SSG horizontal and then do the applied tongue. You might have to modify the tongue a little bit, but then you could place it wherever.
Yeah, that's true.
Yeah. Still have to take care of the bite on the frame above, and that's typically a 1/2 inch, but that's a good point. Whenever we have the possibility of increasing that clearance, like Kyle said, between the top edge of the IGU and the mullion tongue, like Kyle mentioned, sometimes that will require a deeper horizontal, like a 3 or 3.5 inch, so that will change the sight line on the building. But for us, the good thing is that we do have an increased clearance between the top edge of that IGU and the tongue. So actually, Kyle, I hope this presentation also helps you, because you're stuck with this one now.
I'm ready to seal it.
that
I'm
Stuart-
confident when these guys, they
that
explained
Stuart
it
is out
perfectly.
there. Yeah, thanks. Oh, and maybe a topic for another lesson learned, but we can, since we are doing pretty good on time, we can just briefly, Kyle, discuss about the glazing requirement. And I can preface this real quick. This project, as you could see, is using a 1-inch IGU with monolithic glass and airspace and monolithic glass. As Kyle knows best, Texas is one of those states that they have some of the most severe weather as far as wind load goes. So they have this organization called Texas Department of Insurance that have their own requirements as far as safety glazing in hurricane-prone regions. On this particular project, it landed in one location close to Houston,
Come on.
an area that the TDI was close enough that was considered a catastrophe area. However, the latest edition, and Kyle, here's where we can collaborate on this. The latest edition appeared to point the user or the reader of the TDI to ASCE for the designation of where safety glazing is required. And safety glazing meaning a 1 5/16 inch overall makeup of glass. Basically having, instead of a total glass thickness of 1/2 inch, we would be up to 3/4 of an inch, because you have a laminated inboard and a monolithic outboard. So Kyle, if you want, you can take it from there.
Yeah, can everybody see my screen?
Yep, we can.
So in Texas, along the coastline, the Texas Department of Insurance, which is a specialty insurance that Texas has for tornadoes and hurricane prone areas, which is basically the entire state. It's basically a wind insurance provided by the state. But anyways, along the coastline, they have designated this a catastrophe area. So any project that falls in these counties, we really need to pay close attention to, because it probably needs to have that 1 5/16 laminated safety glazing for the building. Now, this is where it gets complicated, because in the presentation they gave in 2018 when they updated the code, they basically said, okay, you just need to go to, it was the AT Council, but then it became ASCE 7, hazard tool, and basically follow what 716 is saying for impact requirements. So if ASCE 7 is saying you don't need to have impact glass, TDI is following that with their new updated codes in 2018. However, this is where it gets complicated, because TDI is not a perfect system. They have inspectors, and the inspectors don't necessarily work for TDI. It could be a private individual who has a PE. It could be a company like us, and they are the authority over TDI for that particular project that they've been assigned. Because of that, they may overrule this documentation that TDI has, saying that you can use ASCE 7 for determining if impact glazing is needed or not, and they may force the issue that regardless, they want to have impact rated glazing on the project. It's very important to get on these projects early, and we've worked with a lot of clients down in Texas and have informed them of this, and they do get involved pretty early, even during the bidding process, to determine what glazing makeup is going to be required. And sometimes they get multiple answers that are conflicting. And then they come to me, and the architect says, according to ASCE 7, we can do this. I'm like, I agree. And then the GC said, I talked to the TDI people, and the TDI people said it's this. I said, you need to talk to the TDI people and confirm with them and fight with them if that's what you want. Otherwise, what TDI says is going to have to go. Even if it's a cost impact on the project, they're the authority on what glazing makeup we can use. So it gets complicated in Texas along the coastline for sure, because they like to follow testing reports as well. In fact, they for years adopted the Florida product approval system to qualify systems being used in this catastrophe zone. They now have their own testing authority that they use. We've had projects in the past that have unfortunately went away because the TDI inspector only wanted to use the testing report. What happens when you have a testing report that maxes out at 12 feet and your curtain wall's 80 feet on a tall building? What do you do with that? And TDI, on the projects I've worked, had no answer for it. They just said my responsibility is to use the testing report to approve this curtain wall. But the curtain wall doesn't match the testing report, and for us, the projects went away, and I have no idea what ever happened to them because they weren't going to accept our calculations. But TDI is a very crazy program. I understand why it's in place, but I think there's some room for improvement, and that's all I'll say.
So yeah, anytime anyone in the office has a project in Texas, and especially if the project is in any of the counties that border the Gulf of Mexico, we need to pay close attention to what the requirements are for the glazing part of it. So run things by Kyle and Stuart. They both have a lot of experience in this area, and do make an effort at the beginning of a project whenever you have a project in Texas to run, to make sure that there aren't any TDI requirements.
It was a challenging project, so I really enjoyed it.